Let us come to the point. Non-linear space. Non-linear space. Let n be a complex or n be a complex or real vector space, or we can say it is a linear space. Linear space. And let this one, it is a function, be a function from n to r, and for all xy belongs to n and alpha belongs to c or r, we have first condition, norm x is greater than or equals to 0. Second one, norm x is equals to 0, implied and implied what x is equals to 0. Third condition, norm x plus y less or equals to norm x plus norm y. And fourth one, norm alpha x is equals to mod alpha norm x. Then the function is called norm on x. Then the function, this one, is called norm on x, sorry, yeah, and the pair, this one, n and this, is called a complex or real norm linear space. Here, non-linear space, it is just like our metric space. Their metric is defined on that side x. Here, non-function is defined on n of n. Here, let n be a complex or real vector space or linear space, and this is a function, new function we define here. Let this be a function from n to r, and for all xy belongs to n and alpha belongs to c or r. We say if it satisfies following axioms, norm x is greater than or equals to 0, just like metric d of xy is also greater than or equals to 0. Second one, norm x is equals to 0, implied and implied by x is equals to 0. In metric d of xx is equal to 0 if and only d of xy equal to 0 if and only x is equals to y. Here, norm x plus y, that is a triangle inequality. Norm x plus y, that is base or equals to norm x plus norm y. And last condition is alpha into x, norm of alpha into x is equals to mod alpha norm x. If these conditions satisfied by this function, then the function is called norm on n, and the pair, this non-empty set n together with this function, is called complex or real non-linear space. Let us take first example on it. Say let, here also, theorem, let n be a non-linear linear space and let D be a function from n cross n to R defined by d of xy is equals to norm x minus y. Then show that D is a metric on n. D is a metric on n. Means this D defined by like this, norm, that D defined in terms of norm. We show that this D is a metric on n. So, proof 1. Here, first condition. We show that D is a metric on n. First condition is d of xy is greater than or equals to 0. Here d of xy. The definition of d of xy is norm of x minus y. So it is norm of x minus y. By actual definition of norm x, first condition of norm x is that is always greater than or equals to 0. So obviously norm of x minus y is also greater than or equals to 0. Norm of x minus y greater than or equal to 0 means d of xy is also greater than or equals to 0. This is the first condition of metric. Second one, d of xy is equals to 0. Implied and implied by x is equals to 1. So okay, d of xy. But the definition of d of xy is norm of x minus y. So substitute there. Norm of x minus y equals to 0. But as we know, norm x, second condition of norm x is equal to 0, implied and implied by x must be equals to 0. Here we can write here x minus y equals to 0. If this x minus y equals to 0, that means x is equals to 1. X is equals to 1. This is the second condition of metric. Now third one. What is third one? That is d of xy less or equals to d of xz plus d of zy. Where d of xy is actual definition is norm of x minus y. And this is again norm of x minus y, x minus add and subtract z minus 1. So after this, here we can apply triangle inequality. So this is less or equals to, there is a triangle inequality defined in norm x minus z plus norm z minus y. But again, by using the definition, this is norm of x minus y is d of xy. So norm of x minus z, that is equals to d of xz, and norm of z minus y, that is d of zy. So okay, so means it is, that is equals to, it is d of xz plus d of zy. But this is the value of d of xy. D of xy is equals to this one, this is equals to this is less or equals to, and this is again equals to. Therefore, d of xy is less or equals to d of xz plus d of zy. This proves the conditions of metric, so that this definition is this function defined by like this that form a metric. So this d is a metric, we can say. Therefore d is a metric on m. D is a metric on m. Now we will stop here.